The chapter begins with time series structure, stationarity, and transformations. We then develop autoregressive and distributed lag models, unit root tests, robust inference, forecasting, software, and the moving average, autoregressive moving average, and integrated extensions. Time series data observe one unit repeatedly through ordered periods. That distinguishes them from a cross-section of many units at one date and from a panel of many units over several dates. Swedish output, the spread of a disease, and inflation are examples. Order matters because nearby observations are commonly dependent. We cannot treat output this quarter and last quarter as unrelated draws, so both models and standard errors must respect temporal dependence. Our goals are to decompose a series, assess stationarity, interpret autocorrelation, estimate autoregressive and distributed lag models, test for unit roots, use autocorrelation consistent standard errors, produce forecasts, and implement the workflow in R and Python. Time dependence changes ordinary regression practice. In a cross-section, knowing one observation often tells us little about another. In a time series, current output is informative about next quarter's output. Serially correlated errors make conventional least squares standard errors unreliable. Random sample arguments no longer apply directly. We therefore need models that include lags, such as autoregressions and distributed lags, and standard errors that remain valid when residual dependence persists. Theoretically, the observed sequence is one realization of an underlying stochastic process. We cannot repeatedly rerun the history of Swedish output to obtain independent samples. Instead, inference relies on ergodicity. Time averages from one sufficiently long realization converge to population quantities. Stationarity provides the stable probabilistic structure needed for that argument. Without it, moments can change over time, and the usual large sample results behind regression and forecasting may fail. A macroeconomic series can contain 4 components. Trend is long-run direction, such as rising output. Seasonality repeats at fixed calendar intervals. Cycles are irregular medium-term movements, including business cycles. The random component is what remains unexplained. Not every series contains all 4. Identifying which components are present guides transformation and model choice. Remove or model seasonality, difference a stochastic trend, and avoid asking a stationary model to explain a changing mean. A moving average smooths short-run fluctuations by averaging neighboring observations. A longer window produces a smoother series but reacts more slowly to change. For quarterly data, a 4-period or multiple of 4 window can remove seasonal effects. For monthly data, 12 is natural. The centered formula gives the endpoints half weight when the window length is even. This is a descriptive filter, useful for revealing trend, not by itself a model for inference or forecasting. For Swedish quarterly output, the raw series mixes trend, seasonality, cycles, and noise. A 4-quarter moving average removes the repeating seasonal pattern and makes the long-run rise and major downturns easier to see, including the crisis of the early 1990s and the decline after 2008. Average quarterly growth is around 0.5%. Remember that smoothing describes the history. It does not create a probability model for future observations. Weak stationarity requires a constant mean and an autocovariance that depends only on the distance between 2 periods, not on the calendar date. Setting the lag to 0 gives constant variance. Intuitively, the series should have the same probabilistic appearance wherever we inspect it. Output in levels typically violates this condition because of its upward trend. Log-differenced output, which resembles a growth rate, is a more plausible stationary series. Stationarity is not a technical decoration. Under stationarity and sufficiently weak dependence, time averages converge to population means, least squares estimators can be consistent, and central limit arguments justify inference. With non-stationary variables, a regression may be spurious, test statistics may not follow their usual distributions, and apparently significant relationships can be meaningless. The practical rule is simple. Inspect and test the series, then transform non-stationary variables before fitting conventional dynamic models. The autocorrelation function measures correlation between the series and its own lagged values. The sample version compares deviations from the time average at two dates separated by a chosen lag. A stationary short memory process usually has autocorrelations that decay quickly towards zero. A non-stationary series often decays very slowly. The full sequence across lags is more informative than one coefficient because its shape reveals persistence, seasonality, and clues about a suitable dynamic model. Swedish output in levels has a slowly decaying autocorrelation, still substantial after many quarters, which points to non-stationarity. The sawtooth pattern at multiples of 4 signals quarterly seasonality. After taking log differences, the autocorrelation falls quickly and is near zero beyond the seasonal lag, making stationarity more plausible. Use the autocorrelation plot both as a diagnostic and as a guide to which lags might matter in a subsequent autoregressive model. A first difference subtracts the previous value and removes many stochastic trends. For an economic series that grows proportionally, the log difference is more natural because it approximates the percentage growth rate. After differencing, return to the autocorrelation function. The transformed series should lose the slow decay of the level. Differencing is not automatic improvement, it changes the estimand, so interpret the resulting model as one for changes or growth rather than for the original level. A deterministic trend follows a fixed function of time plus a stationary disturbance, so including time as a regressor can remove it. A stochastic trend evolves through accumulated random shocks. Swedish output growth varies across decades in ways a single linear time trend cannot capture, so differencing is more appropriate. Distinguishing the two matters. Detrending a random walk leaves non-stationarity, while differencing a truly deterministic trend may discard useful long-run information and create unnecessary noise. An autoregressive model of order, one predicts the current value from the previous value and a new shock. Stationarity requires the slope's absolute value to be below 1. Under that condition, the process has a constant mean, finite variance, and autocorrelations that decay geometrically. The model is estimated by least squares, using the lagged outcome as a regressor. A coefficient near 1 signals extreme persistence and raises the possibility of a unit root. Forecasting from the first-order autoregression is recursive. The one-step forecast uses the latest observed value. The two-step forecast substitutes the first forecast where the next lag would appear, and longer horizon forecasts repeat the process. Only the latest observation is needed because of the model's Markov structure. As the horizon grows, the effect of that observation decays under stationarity. The forecast moves toward the unconditional mean, and uncertainty increases. A higher-order autoregression includes several past outcomes. It can capture richer dependence and seasonal patterns, but each extra lag costs observations and parameters. Stationarity is now a condition on the roots of the lag polynomial. For a second-order model, the slide gives simpler coefficient inequalities. Estimate the model by least squares using a common sample across candidate orders, and choose the number of lags with an information criterion rather than maximizing in-sample fit. The Akaike information criterion combines fit and complexity. A lower residual sum of squares improves the score, while twice the lag order penalizes additional parameters. It therefore formalizes the bias-variance trade-off. To compare orders fairly, estimate every candidate on the same set of dates. Otherwise, a shorter model benefits from more observations. Select the order that minimizes the criterion, and for quarterly data, include seasonal candidates such as lags at multiples of 4. For log difference Swedish output without seasonal adjustment, the first-order coefficient is negative because an unusually high-growth quarter tends to be followed by a lower one. The information criterion prefers 4 lags, and the fourth lag coefficient is positive, indicating correlation with growth 1 year earlier. That pattern is consistent with residual seasonality. It is a reminder that model order often reflects the measurement frequency and calendar structure, not merely abstract statistical convenience. After seasonal adjustment, the dynamics look different. The first lag coefficient is positive, suggesting business cycle persistence. A second-order model substantially improves the information criterion, and the second coefficient is negative after controlling for the previous quarter, indicating partial reversal at a 2-quarter horizon. As in multiple regression, each autoregressive coefficient is a holding other lags constant effect on the conditional mean, not the simple correlation between the series and one lag. An autoregressive distributed lag model adds lagged predictors to lags of the outcome. Those extra variables may improve forecasts if they contain information not already present in the outcome's history. Both the outcome and predictors should be stationary, and their lag lengths may differ. Information criteria can guide the choice. The framework extends naturally to several predictors, each with its own lag pattern, but a large lag search can overfit and should be validated carefully. Granger Causality asks a predictive question. Do lags of one variable improve forecasts of another after controlling for the latter's own lags? Test the joint null that all added lag coefficients are 0. Rejection means the first series has marginal predictive content. It does not establish a causal effect in the design-based sense. Markets may anticipate future conditions, and both series may respond to emitted forces. Use autocorrelation consistent inference when the residuals remain serially dependent. A random walk is the boundary case of a first-order autoregression with coefficient 1 and no intercept. Each value equals the previous value plus a new shock. Its variance grows over time, so it is not stationary, even though a realized path can appear to trend smoothly upward or downward. 2 independent random walks often look strongly correlated by chance. This is the source of the classic spurious regression problem. The simulation makes spurious regression vivid. 2 completely independent random walks produce a sizable negative sample correlation and an extraordinarily small conventional p-value. We know the relationship is false because the series were generated independently. The test fails because unit root processes violate the stationary assumptions behind its reference distribution. Never regress non-stationary levels on one another without first checking stationarity, considering differences, or analyzing a possible cointegrating relationship. The Dickey-Fuller test rewrites the first-order model in changes. A unit root corresponds to a 0 coefficient on the lagged level. Stationarity corresponds to a negative coefficient. The augmented version adds lagged changes to absorb serial correlation. Its statistic does not follow the usual t distribution, so special, more negative critical values are required. The null is non-stationarity. Rejecting supports stationarity. Failing to reject is not proof of a unit root, especially in short samples. Even after modelling lags of the outcome, regression residuals may remain serially correlated. When adjacent errors move together, conventional least squares standard errors are often too small, producing inflated statistics and excessive rejection. The coefficient estimator may still target the desired conditional relation, but inference is wrong. Heteroscedasticity and autocorrelation consistent standard errors, often called Newey West, estimate uncertainty while allowing both changing variance and serial dependence up to a chosen lag. The Newey West estimator combines residual products across nearby lags using Bartlett weights that decline with distance and reach 0 at the truncation lag. A common rule sets that lag near the cube root of the sample length. A larger value captures more persistent dependence but adds estimation noise. The choice should reflect frequency and residual diagnostics. Autocorrelation consistent does not mean always larger, it means consistent for the dependence pattern allowed by the estimator. The Swedish growth example demonstrates that last point. The coefficient is unchanged because only the variance estimate changes. The conventional standard error is about 5/100ths, while the Newey West value with 5 lags is about 3/100ths. Here the robust error is smaller. In many applications it is larger. We should never justify the method by saying it is conservative. We use it because it targets the correct sampling uncertainty under serial correlation. A model for log differences forecasts growth, but users often want the future level. Reconstruct the log level from its predicted change, and then exponentiate. Because the exponential is nonlinear, the conditional mean needs the log normal correction involving half the forecast error variance. Prediction intervals must also reflect the variance of the multi-step forecast, which grows with the horizon. Back transformation therefore requires both the point forecast and a careful treatment of uncertainty. The R preparation reads Swedish output, declares a quarterly time series, creates the lagged level, and computes the log difference multiplied by 100. That transformed variable is approximately quarterly percentage growth. Declaring the frequency is important because it preserves the calendar structure used later for seasonal interpretation. Always verify alignment after constructing lags. The first transformed observation is missing by definition, and every subsequent row must pair the correct dates. The next R page fits the first-order autoregression as an ordinary regression of growth on its lag. An alternative function searches several autoregressive orders and selects one by the information criterion. Turning off demeaning while retaining an intercept reproduces the intended specification. The two approaches are complementary. The explicit regression makes the model transparent, while the dedicated routine manages lag construction and order comparison. For autocorrelation consistent inference in R, compute a Newey West covariance matrix for the fitted autoregression and pass it to the coefficient testing function. The distributed lag test uses the same covariance choice in a joint WALD test. The lag parameter sets how far residual products enter the variance estimate. Reporting it is essential because a different truncation choice can change the standard error even though the fitted coefficients remain fixed. The unit root code applies the augmented Dickey-Fuller test to log output in levels and to its log difference. The expected pattern is failure to reject for the level and rejection for growth. The null is a unit root, so the logic is the reverse of many familiar tests. Also remember that the displayed software p-value uses specialized Dickey-Fuller approximations. Comparing the statistic with an ordinary t-critical value would be incorrect. Python creates a quarterly period index, turns output into a time index series, and computes the log difference. Making time explicit helps prevent accidental reordering and makes future forecasting dates intelligible. As in R, the first value disappears after differencing. Before estimating any dynamic model, inspect the resulting index and missing values. A perfectly coded lag regression on misaligned dates answers the wrong question. The Python first-order model uses least squares on growth and its lag, then requests autocorrelation consistent results with 5 lags. This changes the covariance matrix, not the coefficient. The code is intentionally close to ordinary regression, so you can see that robust inference is an additional layer. Compare conventional and Newey West standard errors, but interpret the coefficient only after confirming that the transformed series is plausibly stationary. For order selection, Python fits autoregressions from 1 through 5 lags on the same effective sample. Holding back the first 5 observations ensures that the information criteria are comparable. The candidate with the lowest Akaike value is retained and its summary displayed. This common sample detail is easy to miss. Without it, Shorter models would be evaluated using more dates, mixing model quality with a change in the sample. The final Python workflow runs the augmented Dickey-Fuller test on the transformed series, fits a 4-lag autoregression, and produces forecasts 4 quarters ahead. The unit root test checks whether modelling the growth rate is defensible. The forecast call then iterates the fitted dynamics beyond the sample. A usable forecast should include dates and prediction intervals, not only the printed point values, because uncertainty expands as the horizon lengthens. A moving average process represents the outcome as a weighted sum of the current shock and a finite number of past shocks. It is always weakly stationary when shocks have constant variance. This is a model of dependence, not the descriptive moving average smoother introduced earlier. Autoregressive moving average models combine lagged outcomes with lagged shocks, and integrated versions add differencing. Together, these models form the Box-Jenkins framework. For a moving average process of order Q, the autocorrelation function cuts off after lag Q, while the partial autocorrelation decays. That signature reverses the one for a pure autoregression, whose partial autocorrelation cuts off and autocorrelation decays. These are identification clues, not mechanical proof. In finite samples, both plots are noisy, and information criteria plus residual diagnostics should confirm the tentative order suggested by their shapes. An autoregressive moving average model contains both lagged outcomes and current or past shocks. Stationarity requires the autoregressive roots outside the unit circle. Invertibility imposes the analogous condition on the moving average roots. With both components present, neither correlation plot has a sharp cutoff. Both typically decay. Select orders with information criteria and parsimony. A low-order mixed model can often describe persistence more economically than a long autoregression. An integrated autoregressive moving average model handles non-stationarity by differencing before applying the stationary model. The middle order records how many differences are required. 0 reduces to an autoregressive moving average model, 1 is common for a unit root series, and 2 would be used only if a second difference is needed. Differencing is part of the model, not a pre-processing detail to forget. Forecasts must later be accumulated back to the original level. A practical integrated model workflow has 4 steps. Test for a unit root to choose the differencing order. Inspect the autocorrelation and partial autocorrelation of the difference series to propose autoregressive and moving average orders. Fit several candidates and compare information criteria. Finally, diagnose the residuals. A model is not adequate merely because it converged or had the smallest criterion. Its residuals should resemble white noise. Box and Jenkins formalized this as an iterative cycle. Identification uses plots, stationarity tests, and correlation functions. Estimation fits candidate models, often by maximum likelihood, and compares the information criterion. Diagnostic checking examines residual autocorrelation, the Ljungbox test, and distributional plots. If residual dependence remains, return to identification and revise the model. The process ends only when the unexplained component behaves approximately like unpredictable noise. The Ljungbox statistic aggregates the first several residual autocorrelations and tests the joint null that they are 0. A small p-value signals remaining serial structure and an inadequate dynamic specification. Passing the test is not proof that the model is true, but it removes one obvious failure. Both languages provide automated routines, yet you still choose how many residual lags to test and should relate that choice to the sampling frequency. Partial autocorrelation at a given lag measures the association between the series and that lag after removing the linear influence of the intervening lags. A pure autoregression has a partial autocorrelation that cuts off after its order, while its ordinary autocorrelation decays. A pure moving average shows the opposite. For a mixed model, both decay. Reading the two plots together provides a disciplined starting point for order selection. The identification rule can be stated compactly. If the partial autocorrelation has clear spikes through a particular lag and then stops, consider an autoregression of that order. If the ordinary autocorrelation cuts off, consider a moving average model. If both tail away, consider a mixed model. Apply this only to a stationary series, usually after differencing, and verify the choice with information criteria and residual checks. Two non-stationary series can still possess a meaningful long-run relationship. They are cointegrated if some linear combination is stationary, even though each series individually has a unit root. Economically, they share a common trend and cannot drift apart forever. Consumption and income, long and short interest rates, and purchasing power relationships are examples. Cointegration is why automatically differencing every variable and modeling changes alone can discard valuable equilibrium information. An error correction model combines short-run changes with the lag deviation from long-run equilibrium. A negative adjustment coefficient means the outcome moves back toward equilibrium after a gap. Lagged changes describe short-run dynamics. This representation preserves the cointegrating relation while working with stationary components. Formal tests such as Granger or Johansson assess cointegration. If no cointegration exists, including the level error correction term would have no stable equilibrium interpretation. Return to Granger causality with careful language. Add lags of one series to an autoregression for another and test their joint significance. Rejection means those lags improve prediction beyond the outcome's own past. It is better to say the variable has marginal predictive content than to say it causes the outcome. Both may respond to a common third variable, and all series must be stationary or handled through an appropriate cointegrated model. Spurious regression arises because independent random walks share persistent-looking paths. R-squared can approach 1, conventional statistics diverge, and residuals remain strongly autocorrelated, even though the true slope is 0. A high fit combined with a Durbin-Watson statistic near 0 is a warning. Remedies are to difference the series, test for cointegration, and use an error correction model when warranted, or avoid a levels regression that lacks a stationary relationship. Forecast intervals widen with the horizon because future shocks accumulate. In a stationary first-order autoregression, long horizon variance converges to the unconditional variance. It does not grow without bound. The one-step interval uses the residual standard deviation, while later intervals include uncertainty propagated through the autoregressive coefficient. Reporting only a point forecast hides this essential feature. A forecast is a distribution whose width changes with how far ahead we look. For log difference models, back-transform the conditional mean with the log normal correction, not by simple exponentiation alone. A prediction interval is created on the log scale and then exponentiated, so it is asymmetric and centered on the median rather than the mean. These intervals are conditional on the fitted model. Structural breaks, policy changes, or misspecification can create additional uncertainty that the formula does not capture. When several time series are modeled jointly, a vector autoregression places lags of every variable in every equation. It supports predictive tests, impulse responses, and forecast error variance decompositions. All variables must be stationary. Unit root variables should be differenced unless a vector error correction model represents their cointegration. Order is selected by information criteria. A vector autoregression expands quickly, so parsimony is especially important when the sample is not long. The R code fits integrated autoregressive moving average models in two ways. An automated routine searches differencing and lag orders using stationarity tests and the information criterion. A manual specification fits one autoregressive term, one difference, and one moving average term. Automation is useful for screening candidates, but the selected model must still be interpretable and pass diagnostics. A lower criterion cannot compensate for autocorrelated residuals or an inappropriate transformation. Our diagnostics combine the residual autocorrelation plot, distributional checks, and the Lungbox test. The forecasting call then produces 4 steps ahead with intervals. Use the residual checks before trusting the forecast. If they show remaining structure, revise the model rather than merely reporting the output. The forecast horizon and frequency should also be explicit. 4 steps means 1 year for quarterly data, but only 4 months for monthly data. The Python fitting page specifies the same integrated auto-regressive moving average order and prints the estimated model. The 3 order entries record auto-regressive lags, differences, and moving average lags. Fit convergence is only the first check. Inspect coefficient stability, information criteria, and residual behavior. The language changes the interface, not the statistical responsibility, to justify differencing and order selection from the observed series. Python's diagnostic plot displays residual autocorrelation and distributional information, while the Lungbox function tests residual dependence at selected lags. The forecasting methods return point predictions and confidence intervals 4 periods ahead. Keep the time index attached so those values map to actual future dates. A good production workflow stores both the fitted model assumptions and the exact transformation needed to convert forecasts back to the original scale. The first summary connects the foundations. A time series follows one unit through dependent periods. Trend, seasonality, cycles, and noise describe its components. Moving averages reveal long-run movement. Stationarity means stable moments and is required for ordinary inference. The autocorrelation function diagnoses persistence. First differences can remove a stochastic trend. An autoregression predicts the current value from past values and is estimated by least squares on the stationary series. The second summary adds the operational tools. The information criterion selects lag order. The augmented Dickey-Fuller test treats a unit root as the null. Newey-West standard errors correct regression inference for serially correlated residuals. Distributed lag models add past predictors. Granger tests assess whether those lags improve prediction. Spurious regression warns that 2 unrelated non-stationary series can look highly significant. Each tool addresses a distinct stage of the workflow. The formula card collects the moving average smoother, sample autocorrelation, higher order autoregression, information criterion, and the Dickey-Fuller rewrite. Read it as a sequence, smooth and inspect the data, diagnose dependence, specify lags, balance fit against complexity, and test whether the level is stationary. The formulas are not interchangeable. Each answers a different question, and their validity depends on preserving temporal order and working with an appropriate transformation. Use the discussion questions to explain what a slowly decaying autocorrelation implies, how seasonal and cyclical variation differ, why non-stationary correlations mislead, why robust errors may be smaller, and what each quarterly lag means in a 4-lag output growth model.